Voyager 1 has now spent nearly half a century traveling farther from Earth than any other human-made object in history. Launched by NASA on September 5, 1977, the spacecraft was expected to complete a mission lasting only a few years. Instead, it became one of the most successful scientific missions ever undertaken. After its historic encounters with Jupiter and Saturn, Voyager 1 continued its journey toward the outer reaches of our solar system. On board, it carried the famous Golden Record, a collection of sounds, music, greetings, and images chosen to represent life and culture on Earth for anyone who might one day discover it. In August 2012, at a distance of roughly 121 astronomical units from the Sun, Voyager 1 became the first spacecraft to cross the Heliopause, the region where the solar wind gives way to the interstellar medium. Although many people describe this as leaving the solar system, it is more accurately the point where the Sun's stream of charged particles no longer dominates the surrounding space. Scientists expected dramatic changes as the spacecraft entered this unexplored environment. While Voyager detected a sharp increase in the density of charged particles, confirming its arrival in interstellar space, another result surprised researchers. The direction of the magnetic field remained remarkably similar to what it had been inside the heliosphere. Existing models had predicted a much larger change, leaving scientists with new questions about the true nature of this boundary. Several years later, Voyager 2 crossed the Heliopause and observed nearly the same behavior. Its measurements confirmed that the transition between our solar system and interstellar space is far more gradual and complicated than researchers once believed. These discoveries did not reveal hidden civilizations or mysterious technology. Instead, they demonstrated that the region surrounding our solar system still contains many unanswered scientific questions. Even after decades in space, Voyager 1 continues providing valuable information across billions of kilometers, showing that patient observation often leads to the greatest breakthroughs. Toward the end of 2023 and into early 2024, Voyager 1 once again captured worldwide attention. This time, however, the excitement was not caused by a new discovery beyond the Heliopause. Mission engineers noticed something unusual in the spacecraft's transmissions. Voyager continued responding to commands from Earth and appeared to be functioning normally, but the telemetry describing its internal systems became unreadable. The incoming data looked almost random, filled with repeated values and meaningless patterns. Online speculation quickly exploded. Some claimed the spacecraft had encountered an unknown force, crossed into another dimension, or intercepted an artificial signal from deep space. The real explanation turned out to be far more impressive than the rumors. After months of careful investigation, NASA engineers discovered that the problem originated from corrupted memory inside Voyager's flight data system, the onboard computer responsible for formatting engineering information before sending it back to Earth. Even though the spacecraft was nearly 24 billion kilometers away, engineers successfully diagnosed the fault, rewrote portions of the flight software, and transferred damaged code into healthy memory locations. Because each radio signal requires more than 22 hours to travel one way, every command had to be carefully planned and patiently executed. Eventually, Voyager resumed transmitting readable engineering data. Rather than confirming contact with an unknown intelligence, the incident became one of the greatest demonstrations of long-distance spacecraft engineering ever accomplished. It proved that a computer designed during the 1970s could still be repaired across interstellar space using careful analysis, precise mathematics, and decades of engineering expertise. The scientific discoveries Voyager continues to make remain equally extraordinary. Its instruments monitor energetic particles, cosmic rays, magnetic fields, and plasma waves in a region that no previous spacecraft has ever explored. After crossing the Heliopause, Voyager measured a dramatic increase in galactic cosmic rays, confirming that the heliosphere acts as a protective shield against high-energy radiation arriving from elsewhere in the Milky Way. The spacecraft also detected unexpectedly dense interstellar plasma, providing scientists with valuable information about the behavior of gas just beyond the Sun's influence. One of its most fascinating observations involved shock waves created by powerful solar eruptions years earlier. These disturbances traveled billions of kilometers beyond the planets before eventually reaching interstellar space, demonstrating that activity on our Sun influences its surroundings much farther than previously believed. Researchers also continue examining the surprisingly smooth transition between the heliosphere and the surrounding interstellar magnetic field. Instead of a sharp dividing line, Voyager's observations suggest a gradual and interconnected boundary. These measurements have improved computer models describing stellar winds around other stars while offering new insights into how astrospheres help protect planetary systems throughout the galaxy. The end of Voyager 1's mission will not mark the end of its importance. Long after its final signal fades into silence, the spacecraft will continue drifting through interstellar space as a permanent monument to one of humanity's greatest achievements. Even without transmitting another byte of data, Voyager will remain a silent explorer, carrying the story of our civilization into the vast darkness between the stars. Scientists estimate that the spacecraft will pass relatively close to another star in about 40,000 years. Its destination is not a planned target but the natural result of its immense speed and the gravitational motion of our galaxy. Although it will never enter another solar system in any meaningful way, Voyager's journey demonstrates the incredible scale of the Milky Way, where even the fastest spacecraft ever built requires tens of thousands of years to approach another star. The famous golden record attached to Voyager's side was never intended as a realistic attempt to communicate with extraterrestrial civilizations. Instead, it serves as a symbolic message, representing humanity at a particular moment in history. The record contains greetings spoken in dozens of languages, sounds from nature, music from different cultures, scientific information, and hundreds of photographs showing Earth's landscapes, animals, and people. NASA scientists understood from the beginning that the chances of another civilization discovering Voyager were extremely small. The spacecraft itself is tiny compared to the immense distances separating the stars. Even if intelligent life exists elsewhere in our galaxy, the probability of a chance encounter remains extraordinarily low. Yet the golden record reflects something deeply human: the desire to preserve our existence and share our story with the universe. Voyager has also transformed our understanding of the heliosphere, the enormous bubble created by the Sun's solar wind. Before the mission, scientists relied mostly on theoretical models to describe this invisible region. Today, thanks to decades of direct measurements, researchers possess a much clearer picture of how the solar wind interacts with the interstellar medium. The heliosphere acts as a protective shield, reducing the number of high-energy cosmic rays that reach the inner solar system. Without this protection, Earth and the other planets would be exposed to significantly greater amounts of energetic radiation. Voyager's observations have helped scientists understand how this shield changes over time as solar activity rises and falls during the Sun's 11-year cycle. Another remarkable discovery involves plasma waves traveling through interstellar space. By measuring these waves, Voyager allowed scientists to estimate the density of material surrounding our solar system with greater accuracy than ever before. These measurements continue improving models of how stars influence their surrounding environments and how stellar winds shape planetary systems across the galaxy. The mission has also provided valuable information about cosmic rays, some of the highest energy particles known in the universe. After crossing the Heliopause, Voyager observed dramatic increases in these particles, confirming long-standing theories about the heliosphere's protective role. These findings help researchers better understand radiation environments that future deep space astronauts may one day encounter. Perhaps one of Voyager's greatest achievements is not a single discovery but its extraordinary longevity. Built with technology from the early 1970s, The spacecraft has survived intense radiation near Jupiter, the freezing darkness of deep space, and nearly 50 years of continuous operation. Every additional day it remains active represents a triumph of engineering, careful planning, and remarkable reliability. Mission engineers continue finding creative ways to extend Voyager's life. As electrical power slowly decreases, they carefully prioritize which instruments remain active, ensuring that the most scientifically valuable observations continue for as long as possible. Every watt of power has become precious, and every successful communication session is treated as another opportunity to learn something entirely new about interstellar space.